Is that something you'll cover, or
we will touch upon it?
okay?
Okay, guys, you are on record now. Go ahead, Albert.
So, are you going to have a class on agents?
So, welcome back, guys. Today is Sunday, the 13th of April. We are going to do a paper reading of. We'll start. We have a few paper readings, but we'll start with MemGPT.
Saturday.
Oh, today's Saturday. I apologize. Today's Saturday, the 13th, and we are going to do the paper reading of MemGPT towards LLM as operating systems. This is a crucial paper. It's really worth knowing about it. I happen to have done a paper reading for a more wider audience. I don't know if I know at least one of you attended that. I apologize if it looks a little bit redundant, but since most of you didn't, and this is a really important paper, I'm going to cover it in detail in the morning. We can go at the pace at which you feel comfortable. In other words, if it looks easy, we can go faster. If it looks harder, but I'm certainly going to go faster than I went with a much wider audience, because I expect that you guys are fully up to speed with all the things that LLMs are about these days. So let me frame the main thesis of this paper. See, we have been looking at, and this goes into the broader category of a reframing of how we look at LLMs. We look at LLMs, if you look at it, 2023 was the year in which the ChatGPT caught everybody's imagination. And to a large extent, language models became synonymous with chatbots, right? Which, because it became a dominant use case from language models and transformers being the playthings of researchers and engineers for serious work, and that would have involved, say, 10,000 engineers and scientists around the world. It went from something of utility to a much smaller audience to reaching quite literally 100 million people, with its becoming utilized as chatbots. The bridge between a language model or a transformer to a chatbot was, would somebody like to remind me, what made a GPT into a chat GPT, for example?
The memory is conversation.
Instruction
fine-tuning, Yashila. Thank you for saying that. It is the Instruct GPT. I was hoping you guys would remember we covered that paper. Remember, that was a crucial thing and the phases were pre-training, supervised fine-tuning, reinforcement learning with human feedback. And that produced something that could have intelligent conversation. Just to recap, otherwise our language model would say, would do a continuation, because language models continue what you give it as input as continuations. Would have continued, what's the capital of France? Instead of saying Paris, it would have replied back and said, what's the capital of Italy? Right? Because that seems just as plausible a continuation. Many lists of such questions or quizzes exist on the internet. So, and Instruct GPT is the one that you use to essentially say, no, it's preferable to answer this question, and so on and so forth. So its basic structure that you have of instruction to tuning, we went that. And so ChatGPTs came out, they caught people's imagination. And yet it remained that large language models, even when they do completions, they can be thought of in a different way. And we are more and more beginning to think of it. People began to use ChatGPT, for example, to write essays, to do things, right? To create summaries and many things. People began to extend the notion of continuation to do actual real things. As people started doing that, and an agentic way of thinking began to emerge, that you saw all of these projects come back. The earliest paper, I mean, I suppose not earliest paper, one of the key ideas was react, reason and act. And you began to see that you could cause an LLM to reason and then to act if it had tools associated with it. So with access to tools, you could then have the LLM act, get back the results of that action, and then continue reasoning forward with it. isn't it? So you could have an interleaving of reasoning and action and reasoning and action till it achieved the goal, a stated goal. Right? These were important milestones in getting things done. But one of the problems that people had as they were reorienting it is that some of the actions people asked for were actions that simply LLMs, the early versions of LLMs, were not designed to. Right? There's a wide gap between a short conversation with a chatbot and asking the chatbot to, for example, reason through a 1,000-page document, right? And find specific answers to specific questions. And people began, as these chatbots, these LLMs caught people's imagination, the uses that they were putting to were such that a chatbot in its traditional form began to look rather a limitation. And so we are now more and more thinking of them as multi-agent orchestration. But this paper in particular, I'll tell you what its main goal is, and then I'll talk about the implications of this paper. What this paper says is that the problem we have is when you use a LLM, a local LLM, right, it has a certain context length, context window length. You can't exceed that. If you exceed that, well, it won't be able to, it just spills over. Now, even if you fit into it, suppose you have very wide context length, the history of our development in the last year has been that very large context lengths had a problem. The problem is the things that were early on in the context and things that were later at the tail end of the context. Whatever you wrote in the prompt early on and whatever you wrote in the prompt in the tail end, that information would strongly color the LLM's response, the language model's response. But the things that were in the middle, so it is something like this. It's the attention that it paid sort of would be like this, right? Early part got a lot of attention. The later part got a lot of attention, but in the middle, you had a lost in the middle. Now, the commercial LLMs have more or less ameliorated the situation, and the evidence seems to be that they don't suffer from it. For example, for GPT-4, there was a research paper. I don't know if you did the research paper reading of that paper or not, but it showed that empirically, you don't have the lost in the middle problem below a token length size of 64K. Now, 64K is a pretty large token length before you start seeing problems of lost in the middle, right? But you and I don't have GPT-4 running on our workstations. What we have running on our workstations are things like Llama 2 and its derivatives, or Mistral, or things like that, or Falcon, and things like that. Right? Pretty much a family of small models. And so the whole question is, these things do have a problem. First of all, the context window itself is small. Right? It stops there. So how do we conquer the world with basically common sense models that you and I can actually use without mortgaging our homes? So, Krishna, your question.
So when I think about that context window, in my mind, for the conversational agent or such perspective, the context that we derive from the vector DB plus the previous conversation we had. So you also
all of that, and we'll talk. Yes. So now, guys, let's come back to it. What this paper talks about is that there are two use cases that it alludes to. One is long conversation. Right? So the way the chatbots behave is that, and if you do that, you ask a question, it will answer. You ask another question. What it has done is it has remembered or it has noted down or say your first question, its answer, and then your question. So it all becomes part of the prompt. And so gradually what happens, your context window begins to fill up. At some point, it will start forgetting because it's a sliding window. It has no recollection of what you said way before. Are we together? There are two ways these things behave. Either it can, if you write it as an application, For example, you must have noticed that at some point, ChatGPT and Cloud and all of these things, they would say enough. We have exceeded the maximum length of conversation we can have, right? Now, I think the problem is getting better. They don't easily say that, but they used to, right? So that's a classic sign that you're spilling over. Or if you're doing it with your own LLM on your machine, you will notice that it has no such notion. So fire up Olama on your machine and then try having a conversation, having a long conversation, and you'll see it just entirely forgot what you said before. Because it only can remember what is in the context window, and it has to be a sliding window. So you're getting that, right? So long conversations are hard to get a handle on. And the second thing is see, do you recall everything that happened minute by minute last week? You don't recall that. We as human beings don't. But what we do recall is the essence of what happened last week, and we can have that, we bring that to bear on our conversation now. Does that make sense? Isn't it? So the fact that we did we inspected a few topics and agents last week has bearing on what we are talking about now. Does inform us, right? Or when you talk to your neighbor, the fact that the neighbor did have a birthday party last week, right? And the child turned X age, let's say, turned 18, and suddenly has now access to driving a car or whatever it is, does have bearing in your conversation that you would have now. So you don't have a way of summarizing that conversation and carrying it forward. Do you see that? Because human beings tend to do that. Okay? Now, if you guys remember our paper reading of the old paper, Simulacra, right? There, you notice that each of the independent agents, so you simulated a village, a small village in which there was a school teacher, there were all of these different roles. And there was a scientist, there was a student, there was a this, there was a that. And each of them, what they would do is, periodically, they would go back and look at their interactions and summarize it. An amazing thing to do. But obviously, they used auxiliary tools to help with that process. Now, there's a resonance of that here. You'll see something like that happening here. What this paper does is it overtly, in a very explicit way, it says we have a way to solve this problem of context window length. And it does it in a very elegant way. And the way it does is it leverages RAG, the techniques of RAGs that you have learned. And therefore, I like this paper because it forms a very good bridge between RAG, retrieval augmented generation, and agentic reasoning. It's a pivotal place in between. Now, this paper has become there's an open source project. So one thing I like about this paper is that it is not just a paper. These people have released the code in GitHub. It's well done. They have also created an entire library. MemGPT is a project framework now. You can just pip install MemGPT and use it. And so one of the things that I ask you to do today is please play with the MemGPT project. That is one exercise to do. Please do that. Otherwise, you'll never get an opportunity to do that. These things are fast emerging and useful. And you may almost argue that, so at this moment, but one of the way they implemented, the way they made it possible, also involved a rethinking of the role of LLM. It is part of the broad rethinking about LLMs that is in progress today. And the broader part of the agentic reasoning discussions that are going on. One commentator very nicely summarized this paper and said that it is about creating an agent that knows or that can manage its own memory. Right? This paper presents you an agent that can manage its own memory. Right? And I believe it was Andrej Karpathy who, right subsequently after that, and in this context, mentioned about this paper and other things that more and more we are thinking of LLMs in the broader context of an operating system, right, as agents. So if you think about, and that's where we'll start with. So those are the two sort of a reference frame or lenses through which we'll look at this paper. One as the big
LLM as a compiler.
LLM as a compiler also, yeah. Yes, so there is an emerging thinking about that, and so how is that possible? See, for that I'll just bring to reference the idea of an operating system. If you look at an operating system, let's say what's an operating system? You have a CPU, and going back to our old notion, you have a central processing unit, right? And I'll spell the word out. Central processing unit. What does it have internally? In a very simplified way, a logical way, it contains the ALU. What does the ALU stand for? Arithmetic logic unit. Right? And of course, all of you have been through computer science courses. You know how we can use D latches and so on and so forth to do our basic operations. And from there, you can build up, right? Transistor to build D latch. From D latch, you can see, or different latches. And from there, you can see how you can do that. And you can have registers. And at the end of it, it is register X, register Y, adding these two up, loading data into one register, loading data into another register, doing for example, a plus operation or something like that. So at its very basic level, atomic level, our CPU does atomic operations with its ALU and its registers. And there is more to it, of course. It has, for example, pipelines of data, and it has the cache, the L1, L2, L3 cache. Okay? And then when you don't find things in the cache, you have a page fault, and you look for data into what is relatively more abundant, a memory, right? RAM, random access memory, right? Think of your DDR5 sticks. Your DDR5 sticks, basically, right? It dips into that physically. If it doesn't find that, there's another page fault, and it then goes into a vast ocean, practically an infinite size ocean of storage, which is your disks, right? Yes. There is a swap space. So let me talk. Actually, we can introduce a swap space also. What it does is, well, okay, if you want to bring that also in. I didn't want to bring that in, but you have a virtual memory, in Windows, or what you call the swap space. What it does is, this is actually a hard disk space, SSD space, right? It is a physical disk space that pretends to be memory, RAM. In other words, the machine, operating systems, they suspect you may run out of memory, and if you do run out of memory, it will swap out those pages that are not least recently used, for example, or some form of it, into a bit of the hard disk that it treats it as a extension. But why would it do that? Because below it is this big ocean of near infinite size that is your storage. It could be local, it could be NFS, whatever, it could be a cloud or whatever it is, that is backing it up. Right? But in that page, searching for anything is hard. But if you keep a very small region, if you just keep a little region of the hard disk, you know exactly where to go look for, and your accesses will be a little bit faster than searching for it in the vast ocean of your broader storage. Right? Now, obviously, as technologies, as hardware changes, operating system design changes, when the hard disks were mechanical, magnetic, which is still true quite a bit, then there is quite a bit of asymmetry between random access and sequential read. Sequential reads you can do at about 100 to 200 Mbps, based on whether you have SATA or SAS drives. You can do random, but random access is always 1/10 the speed. 10 Mbps is about, give or take, is the speed you'll get with random access, right? Things have changed with solid state drives. Now, solid state drives, random access are much faster. Actually, the whole big data movement started from the fact that, based on this asymmetry, the fact that random access reads were so much slower than sequential reads, right? Which is why there was the big famous statement, hard disk is the new tape. In other words, it should only be accessed sequentially. And a lot of these architectures of big data, they tried to create clever ways so that you could do mostly sequential reads and lift things, hot data into memory. For example, HBase keeps a lot of hot data into memory, operational data into memory. So anyway, that is the history of the field. But the bottom line that I'm referring to after this long digression is that at each level, you have, in some sense, the equivalent of a page fault. If you don't find what you're looking for in the register, you dip into the cache, your L1, L2, L3 cache, which run at a slightly slower speed than the actual register, but still pretty fast. If you don't find it in the cache, God forbid, now you're not talking of SRAM now. Now you're talking about the DRAMs, which are way, way slower, but much cheaper. Right? Today, for example, DDR4, 32 gigs of DDR4 is $40, right? As of today, give or take a couple of dollars. Whereas, and DDR5 is a bit more expensive, it's twice the cost, but prices will come down. But 64 gigs of SRAM in the CPU is prohibitively expensive. Right? It's just not really feasible, isn't it? You can go buy yourself a A100 in a GPU and you will get a sticker shock, right? $30,000 or something like that in a H100 or something. Very, very expensive. So that's the thing. But when you go from RAM down to physical disk, again, there is a huge slowdown by a few orders of magnitude. But by the way, we're not just talking 2x slower or 3x slower. We are talking about orders of powers of 10. Right? You go down from memory speed, from CPU speed. By the way, CPU bandwidth is what typically CPU and GPU internal bandwidths are what? They are in the range of
gigahertz.
their throughputs are in the range of 100 gigabit per second, right? And now terabits per second, right? You're talking about terabits per second internal bandwidth. Memory bandwidth is still in the gigabits. SSDs are like tens or hundreds of gigabits nowadays. And that is if you have, like, for example, the NVMe, that is PCI 5 standard, has what? It gives you up to 14 gigabit per second. 14. Right? 14 is still nothing compared to what the CPU internally maintains, terabits per second. And by the way, from there, when you go down to 14 is still very slow, right? From a memory perspective, NVMe perspective, storage perspective. Memory still has hundreds of GB per second bandwidth. Anybody remembers what the typical bandwidth is of DDR5? So anyway, we won't get into that. So what happens is that the way the CPU works is that it is the reasoning unit and it retrieves data as it needs to. The bottom line is there is only so much data that it can maintain in its L1, L2, L3 cache. Does that make sense? And do you see an analogy of this to a LLM? LLM is a reasoning unit, isn't it? It's AI. It's intelligent, or we are not intelligent, but sort of. It is a reasoning unit. If we think from an agentic reasoning, it can reason, but it has a limited context window. Right? So it is almost like small cache, very expensive small cache. But what can it do? It can retrieve things from a much broader memory if it knows how to load the right information. Do we have the technology for that? That technology is RAG, right? That's literally what we do. RAG, when we learned RAG, what was it? Given a prompt, find out what is the relevant data for it, dip into the vast pool of information you have, either vector database, keyword database, search, or traditional database, or just go use a tool to go search on the web, whatever means. Retrieve only the very pertinent bits of information, load it into the prompt, right? Create a much bigger prompt. Are we together, guys? Just a 101 So 101 of RAG, 101 RAG is what? Prompt goes in, X goes in, let's say, it gets augmented, X becomes here, it gets augmented with a lot of search results, and that goes into the LLM. That is RAG, isn't it? And the idea is that these are pertinent information, pertinent to this prompt information, and LLM uses that. So therefore, the basic insight of this paper is that why can't we do that? Here, treat it as an operating system. LLM is the core, right? The CPU. So what is the architecture of a traditional or operating system? CPU, remember, with its very limited space, right? Cache registers, etc. And then I will just simplify memory and disk to let's just call it storage. Vast storage. Is that fair? Right? Somewhere in there is the memory, but vast storage that it reads to. Because as far as it is concerned, there is vast storage through file system and so on and so forth, right? It internally has a scheduler, it's a reasoning machine and so forth. So what they're basically saying is that its analogy is this is your LLM, right? There is a storage. Now, just as you have a file system, a virtual memory manager in an operating system, you remember that you have what do you have? What does the kernel consist of? A scheduler, a memory manager, a file system. Right? This takes care of your processes. This takes care of your memory. And this takes care of your storage. Isn't it? So why can't we treat the LLM sort of like a kernel? Let it be the manager of what it does, sequence of tasks, right? It will do, as well as be the manager of the memory, bring things in and out and so forth. And if we could do that, what comes out of it? So let's see what comes out of it. The best way to see what comes out of it is actually, I would like to go first to this example. Where is the example gone? Okay. Here. Figure 1. Let's look into figure 1. See, this is how this thing is acting. You start a conversation, right? The blue is you. Let's say the conversation starts with a chatbot asking you a question. How was your day today? You say, oh, fine. My boyfriend Jane baked me a birthday cake. Right? So your response is, oh, wow, happy birthday. Up to that point, any chatbot can do it. That looks like normal response, right? But here is something that it says. This is too small an example, and you won't start running out of context window, but it's just illustrating the point. At this particular moment, suppose this is enough, right? You're filling up your context, just hypothetically, this is a toy example. Then what it can do is, it can behave like an operating system. It can recognize that fact and say, we do have a memory pressure, we need to swap some things out. And so what it does is, it maintains something called a working context. Into the working context, it saves two facts. It happens to know what the date now is, isn't it? And what the user gave is this info. For bake me a birthday cake. From this, it infers that there is a birthday. It saves that fact. Birthday is February 7th. Right? And also boyfriend is James. 2 bits of knowledge. Did I give you something like that in your AI newsletter as a... Now, if you had done that, it would have resonated with you. Right? I asked you to extract some knowledge from the thing. But anyway, you guys haven't done that. So we'll make progress. So we go forward. What does it do? It has a working context, someplace where it is storing. Remember, there is the raw trace of the conversation. It's a log. It can store the log. If it can store the log in a durable storage, in a file system, for example, in a database, in some database records or something. I believe in this paper, they store it in PostgreSQL. Right? They can store that. The raw log of the, but the raw log of the conversation is not so useful. Just like when you talk to your neighbor, you don't want to retrieve in your mind every single word that was spoken and said. What you want to retrieve are facts like this. Would you agree? This is of value for you to have a good conversation with your neighbor, isn't it? And it is extracting nuggets from it. You extract it. And so let's read the footnote here. MemGPT left writes data to persistent memory after it receives a system alert about limited context space. Does this make total sense, guys? Right? Then it continues. Let's go to the conversation continues. It will say, did you do anything else to celebrate your birthday? Right. Then your response is, yeah, we went to Six Flags. The user response, we went to Six Flags. Now you realize that you would be stumped. You can just come up with a generic answer that, wow, Six Flags is great. Nice, you had a good time. Right. That would be a generic response. But see what you can do. If you could go, you see the word Six Flags here. You can do a rag on it, isn't it? When you do a rag on it, you end up with search. You first end up with raw logs like this, right? Document. This is your standard document retrieval, right?
Yeah.
You do that. I love Six Flags being like 100 times. In the past conversation, you have said this, right? You have been there like 100 times. Actually, in my case, a bit of issue. We literally used to live next to Six Flags, right? And so we had an annual pass. So while most people take their kids to the neighboring park, whenever we wanted to, our kids we used to literally 3-4 minute drive. We would literally go to Six Flags. Right? And they just assume that Six Flags is just a park. They grew up thinking like that, my kids, actually. So anyway, in my case, it happens to be trivial. We went there 100 times. Right? James and I actually first met at Six Flags. It also remembers that. Because you can remember that conversation, and where did you get it? By ragging it. Do you see the power of the response now the chat can make, the LLM can make? And that is the gist of what it is, what this is about, sorry. That is really, look at this. You realize it will take, just think about it, how differently the response would have been if you could not have ragged Six Flags. Yeah, I'll take questions, guys, but please pay attention to it. It says, did you go with James? It's so cute how both met there. That, even in a neighbor, would look as like pretty nice for the neighbor to remember so much about it, isn't it? Okay, questions. I hear two hands. Yeah, Albert. I see two hands.
Here, the chatbot is asking questions instead of you asking chatbot.
It's a simulation. It's sort of they're making a point here. It's a toy example. They're making a point. Go ahead.
So, sir, this recall storage must be an agent doing that, right?
Yeah, and that's the architecture we're coming to. It's part of the MemGPT is literally the architecture of which recall storage is a part. We'll come to that. Go ahead.
So, are these people, are they telling us that could mean that there is memory agent, there will be one memory agent, or this is a part of multiple memory agents?
No. What it is saying is that think of our LLM in this architecture as the CPU of the core of a operating system. It has, the LLM should have access through RAG to memory. And the document stored that you were thinking of, now you think of it more in you just change your optics a little bit, lens a little bit. You're looking at it in the lens of an operating system. right? That's the title of the paper, Towards LLM as Operating Systems. Right? Now, that is why a gist of this paper can be, as one commentator wrote, it is that MemGPT says it is an agent that manages its memory through RAG. So manages its memory. Go ahead.
I have another question. This birthday, six flags, these token words, how LLM identifies that?
Oh, that's too easy. That is through prompts. You just say from all your conversation. System prompt, you have to write the intelligent prompts that get the keywords out of it and so forth, and rank the keywords.
So that even LLMs can feed you back the keywords like
yes, it can.
like let's say here the conversation could have gone from a baking point of view. Like was it like
it could have gone into baking and cooking and so
cooking and so
yeah. So it's see here they're making a toy example to illustrate a point. Okay. But based on the history, it could have decided to go either ways, right? What it was. So, for example, in the history, there's a whole lot of baking and cooking going on.
Then that's where I am failing to get that. How does it identify the token? Like instead of six flag, it could have gone to the baking form.
Yeah.
So
because the user said that yeah, we went to Six Flags. There is no baking in that state.
But in the previous example, he has said that that person.
Yeah, bake me a cake. So then what it does is, because did you do anything else to celebrate? You realize that this is a exploratory question at that moment, right? It could have gone either way. If it went into baking, it would have continued into baking.
And that's my question is like, how does it prompted this next question? I'm trying to get the brain behind LLM asking a meaningful question.
Yeah, see, it could have either done a question or given a comment or something like that.
I see.
This is the nature of the LLM. I mean, frankly, never forget the fact that these are stochastic machines, right? So there's a certain probability that it could have produced something else entirely.
Yeah.
But it happened to produce this. But the point is not up to here. See, up to here, it is non-impressive, right? Where it gets impressive is, yeah, this answer, therefore.
Yeah, that is mind-blowing.
That's mind-blowing, isn't it? That's really good. Yeah? And now the good question is, yeah, go ahead.
One question. So this special words that it was able to extract and put it in the that working context. The question I have is that you mentioned it's more of a RAG structure. How, unless it pushes back to that vector database that where the internal storage, or whatever the conversation gets stored, how would that decide that these words, are part of that context, that the conversation that's going on? Meaning, where is this vectorization of these words coming into the picture here? You mentioned Postgres SQL, something that they have used.
And PG vector. So for vector databases, they use PG vector, which comes built into Postgres, and they use Postgres to store, I think, the logs.
Oh, got it. So there is this vectorization in between.
There is a vectorization.
Oh, got it.
Yeah, RAG, of course, will be searching into. Typically, you always at least search into a vector database, whether or not you do keyword search and other searches or web search. So that's that.
Yeah, and I'm actually looking for the follow-up question, how it came up with the follow-up question, because that is
a mixture of two things. A good system prompt that you wrote, that's why prompting is important. You see all of the code base is available. Go look into it. It's very well done. And also, that's how LLMs behave. They at the end of it, what can it do? It will ask you a question. It will make a comment. It chose to ask you a question. So, guys, now comes the question. I hope if you're suitably impressed with this first figure, the bait has hooked you.
Yeah.
Right. And now let's figure out what is it made up of. So the main architecture is quite interesting. It's not. When you look at it, the sheer simplicity of it is amazing. Like all great ideas, it is not done by a pastiche of hacking here and hacking there. They've done it with a very simple and elegant idea itself. And literally the architecture is that idea writ large. Look at this part carefully. They're saying that, see, I have a limited token window, right? This is my finite context window. Let's say 8K tokens, right? Or whatever, it doesn't matter, whatever your token is. You first of all, first things first, as you must have learned from LLM 1 and 2, the most important thing is to get your system instruction right, because that is the driver, right? In the world of, if you're thinking of it as CPU, GPU, etc., in an operating system analogy, your system instruction is your kernel code, isn't it? Is like a Linux kernel code. It's the heart of it that will drive it. Do it well, right? Once again, emphasizing the relevance of prompting, right? Good prompt. Write a good one. So MemGPT system prompt. It's read-only, it's static, it never changes, it's forever there. Why? Because the operating system never keeps rewriting its kernel code as it goes on. It's there. It's the background that drives everything. Then what happens? Your working context is what you think of, this is the working context. It maintains a set of, it has limited space, right? It maintains the working context, facts that are relevant, it maintains there. And then it has a FIFO queue. What is the FIFO queue? Those messages that are coming in, right? Yeah. First in, first out. It just maintains a sequential list of those messages. But soon you will run out of space. So what will it have to do? You need a queue manager that will take those messages and store it somewhere. A recall store, right? A log of those conversational steps that have happened. More importantly, you also have a function executor and you have an archival storage. So this is your basic RAG, the RAG framework. Ultimately, right, if you look at this layer, think of it as this storage and this storage as the storage. What is your function executor? This is your function calling. You can do function calls on it and so forth. Yeah. Do I hear somebody?
To get the search results?
Yeah, okay. To get the search results, to do things, to function call. Now, what happens is that, I'll give you an example. Suppose you want to do something that is multi-step. You want to know, what's the weather here today? Well, now first you have to figure out what is today. Here, right? What is here? Right? And then dip into somewhere to find out what is the historic weather patterns, or just look up something, right? Or call a function or something like that. So, and then retrieve that and then do it. So that's the important part. The output that you produce is not directly something you see. It can trigger, the LLM produces something, but then you need a parser to parse it and determine if it leads to further function calls. It has to. So you have, and you see that agent thinking in full-fledged. And I think there's a picture somewhere here that shows that. Where is that? Or is it not even here? Okay, it's mentioned. It's probably not drawn as a picture, but you should just assume that that is there. Now, guys, I will go through this a little bit more carefully. Yeah? So it talks of a memory hive. So, okay, let us read through the introduction carefully. In recent years, large language models and their underlying transformer architectures have become the cornerstone of conversational AI and have led to a wide array of consumer and enterprise apps. I hope you agree. Despite these advances, the limited fixed length context window used by LLM significantly hinders their applicability to long conversations or reasoning about long documents. For example, the most widely used open source LLMs can only support a few dozen back and forth messages or reasons about a short document before exceeding their maximum input length. Right? Think Llama. Directly extending the context length of transformers incurs a quadratic increase in computational time and memory cost due to the transformer architecture's self-attention mechanism, making the design of new long context architectures a pressing decision. Well, things have changed a little bit since this. I mean, Gemini 1.5. Yeah. See, people talk about ring structures and so on and so forth to do that. But see, all of that is great. It's like looking at the stars. You can't go to the stars. All of these commercial LLMs are not something you and I can afford to build in our laboratory. So let's be practical. So this is still a problem. Was it?
Infinite context.
Yeah, I saw that. Actually, tell me a little bit more about it.
No, the context is like you can have a
Infinite context.
They keep rotating.
Through rotation. Yeah. Okay.
Gemini 1.5, 1 hour of video.
It can do. Yeah. So people here in the audience are pointing out that context windows are increasing in the commercial ones. Again, as I said, lovely, but how can I get my hands on it in the lab? So that's a problem. So while developing longer models is an active area of research, etc., I will skip over all of that. I hope we have made the point. In this paper, we study how to provide the illusion of a infinite context while continuing to use fixed context models. See, in my view, right, even though the context window problem may get solved, even for this, the basic idea that you should reorient your thinking and think of LLMs more as pieces of our operating system, I think, and as agents, I think that is here to stay. The source of this whole investigation was context window. It's all right. Context window problems may get solved. But we are, the main contribution of this paper, you will remember, in this reorientation of thinking about them as OSs. We leverage the recent progress in function calling abilities of LLM agents to design MemGPT and OS-inspired LLM for virtual context management. Does the word sound so much like virtual memory management, right? Using function calling, blah, 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 these capabilities allow for to page. Now, if you are doing operating system theory, you must be familiar with the word of paging in and out relevant information. And literally they use that sort of word, right? And I apologize to those of you who don't have background in OS theory. Just take it as bringing in relevant information and taking it out. That's it. So now the main context is made up of the three parts as the picture shows. The system instructions are read-only, static, contain information on the MemGPT control flow. Now, you guys all have learned about the relevance of system prompts. Hardly needs to be spoken, right? The system is, the intended usage of different memory levels and instructions on how to use the. So think of it as the kernel. Is the kernel of your operating kernel code. Working context is a fixed size read-write block of unstructured text, writable only via MemGPT function calls. Right? So what is the MemGPT function call into which the working context is run? Look at this example. Do you see this working context being written to by LLM? Right? It is right into that. So that's it. Remember, it is not a direct log of the conversation, but it is nuggets taken from the conversation. That is one thing to remember.
And that too, LLM is actually adding that context. So
that is.
Does that have a context window size too? Like
no, your total context window is broken up into three parts. No, the total context window that you have. So you have to be careful. You have to ration it.
Yeah.
Keep some space for system instructions, but don't write your system instruction to be so vast that there is no space left.
And working context and then LLM generated context.
And then, and then the normal conversations are happening that you're storing in your FIFO. Right? So this thing, then this, it's all here in your FIFO.
This FIFO cube context also plays
right, exactly. Yeah. Yeah, and yeah, because see, look at this. This whole thing put together is your context window. Right? So now let's come back to it. Working context is a fixed size, read, write, of unstructured, etc. The FIFO queue stores a rolling history of messages. So this is the back and forth you're having, right? So we understand this architecture, guys. Simple, right?
There should be flush.
Exactly, and that is here. That is the queue manager. Queue manager is going to flush it. The queue manager manages messages in recall storage. Where is it flushed to? Recall storage. Right? And the FIFO queue. So it does the back and forth between. When a new message is received by the system, the queue manager appends the incoming message to the FIFO queue, concatenates the prompt tokens, and triggers the LLM inference to generate the completion tokens. So far, so good. The queue manager writes both the incoming message and the generated LLM output and outputs to recall storage. So there is an actual database, messages database. Right? when messages in recall storage are retrieved via MemGPT function call, for example, the RAG and so forth, the queue manager appends them to the back of the queue to reinsert them into the LLM's context window. You see the architecture. You see how simple it is, guys. Dead simple. What a brilliant idea. What a brilliant idea that you can do it in that. So the queue manager is also responsible for controlling blah, blah, blah. I won't go too much into it. You got the gist of it. Function executed. MemGPT orchestrates data movement between main context and external context via function calls that are generated by the LLM process. Good. Right. Memory edits and retrievals are entirely self-directed. MemGPT autonomously updates and searches to its own memory based on the current context. For example, it can decide to when to move items between contexts, right? Histories and so forth. Guys, I won't go into that. You have gotten the gist of it, but let's look at the results. And the results will control flow, etc. An example of conversation snippet when MemGPT left updates stored information, right? So you can replace. Oops. So, how was James doing? Any special plans today? Actually, James and I broke up. Context immediately does a replacement. Okay.
February 14th.
Feb 14th.
That's
It's just how to happen.
Valentine's Day.
So sorry, yes, this can we the context tokens?
Don't ever bring it up.
Yeah.
Hmm?
So what is that? I'm not getting the context token and window messages. What is that?
No. See, working context is the nuggets, the gems that it holds to. Think of it, right? The meaningful memory that it needs to have as a background to talk to the user, right? And so in that working context, remember, initially it wrote, look at this, it wrote, boyfriend name is James on Feb 7. But then the moment it realizes that it was a breakup,
Changing.
yeah, it needs to go edit that back.
Just throw it off.
Yeah. So this is it. Sorry to hear that. Hope you're okay.
Within 7 days.
Within 7 days.
Asif, while
Yeah.
this is so fascinating, my mind is literally spinning around two things. One, the danger of this. The danger in the context of, we all know how social media, is kind of influencing for, kids sex trafficking and all that stuff. It's very easy for somebody to build agents to kind of have these very sweet talks with, with underage and, persuade. That's one. The second most important thing that was going through my mind was about the social engineering. It's extremely easy with this if that memory is kind of allowed to happen, to kind of social engineer, attack,
Yeah.
and that's a real danger, right? Just
Right.
trying to throw a couple of these scenarios in, though this looks like damn fascinating.
No, it is certainly. You see, guys, with AI, the people who are really concerned with it, in fact, those researchers who created this very good documentary called The Social Dilemma. Has anybody seen this documentary called The Social Dilemma? I hope you would agree that it does raise deep questions. It's scary. I mean, as a digression, I would invite all of you to go watch that documentary, The Social Dilemma.
Where is it? Netflix?
YouTube. And Netflix.
Where is it?
Yeah, it's in Netflix. Yeah.
It's on Netflix.
There's also coded biases.
Coded biases. Okay, hey, post those links. Let's all share it. Please post it. Post those links. So coded biases. So these researchers who did that, or the people who made that movie, they have an organization that literally looks at what we need to be careful. What is the harmful effect of AI on human society if we are not careful? And they, in a recent interview that I watched, they talked about, actually not so recent, months ago, they talked about AI's biggest problem being, generative AI's biggest problem being, it is causing a complete collapse of reality. We don't know what is real and what is fake. So remember, every time you celebrate the fact that whatever is the latest thing, Sora coming up with very realistic scenes, the flip side is also, now, how would you know a reality? How would you be able to do? On a podcast I watched, I listened to, it said that they put videos before human beings and asked them to tell whether it was Sora generated or whether it was actual human produced videos. Humans failed miserably. They couldn't tell. Right? So there is obviously, to Madhu's point, a grave danger. Right. So somebody once told me a very interesting fact. It says falsehood always wins the day. Truth may win the age in the long term, but on a given day, people are swayed and always believe the falsehood. The reality of the day is always false. Why? I think it's a Greek saying that says, by the time truth is tying its shoelace, falsehood has already gone around the world. So, and now the dangers of that are there. Yeah.
When in the working context with the staff, here as the question for expected, what if it is placed in reverse? Like James is the person, or James is the name of the person. Would it still be able to look for that?
That's a good question. Patrick asked that, what if the statement is phrased differently? Or would it be able to? I think the system prompt here is robust enough because it says that in view of every new fact, revise your entire working context.
Well, as long as it's the same LLM you're using
yeah, it can do that.
Follow the same.
That is right. Yeah. Having said that, it is also true that they are bringing in their best examples. It's a paper, so it is. But people have tried out MemGPT. They're very happy with it. I mean, it's a very successful open source project at this moment.
Imagine a fine-tuned version, they're much better.
Much better for specific case. And that's the beauty of it, because the LLM is the LLM. You can bring in your own fine-tuned LLM to this architecture.
And from an architecture perspective, if we were to introduce like a graph database for this, like that piece of capacity, it's like concepts themselves. Then like it kind of has like a reversible relationship with them. So then you can search by nodes and like the edges and stuff.
Actually, that's a very insightful point. Sheila mentioned, if you have a graph database, and let me emphasize the word graph in there, graph database, which specifically encodes relationships, which will be far more intelligent in capturing it. Certainly true.
In fact, I saw a video where this graph database is generating the prompts, next prompt.
Absolutely. So this statement from the audience that there's a video that shows how graph databases can prompt them. See, guys, forget database. Graphs are powerful things and underappreciated. They have always been sort of a niche area in computer science. More and more, the big discoveries that are happening, especially in AI, are deeply informed with graph.
Llama index graph.
Yeah, Llama index. Okay, so Praveen mentions Llama index now has a graph. Right, I didn't know that. Okay, so I learned something. Good. So guys, could you post a link to that? No, just post if you don't mind posting a link. Right? Guys, as you bring in your nuggets, right, it helps if you post it on Slack because then all of us benefit. Yeah, go ahead.
So the example that I have here is basically Linda and named entity all over the user.
It's not named entity itself, but something similar. Let's say you can read up the system prompt. Actually, the whole code is open source.
Yeah. Asif, there's another thing called the KV caching. Have you heard about it?
Oh yeah, key value cache. So I have heard. In fact, I would love to. Have I not covered it already in the LLM one? I didn't, right? I would be happy to do the paper reading on that. It's a very important topic. It's big. So, but let's keep it for another day. So, guys, I want to wind down on this paper. And by the way, one more thing, I will post a quiz on this paper before the end of the day. If you want, just use it as a review. So look at this, guys. These days we say that the state of the art is GPT 3. Let's say initially it was 3.5 turbo. A deep memory recall. In this task, the agent is asked a specific question about a topic discussed in a prior conversation, like way before. Right? The agent's response is scored against the gold answer. Now, what is the gold answer? I'll explain in a moment. But just say, magically, there's a perfect answer. MemGPT significantly outperforms the fixed context baseline. Right? So you notice that if I just use the GPT 3.5, its accuracy is 38%, means 2/3 of the question broadly, it gets wrong. Like 2/3 of the time it's clueless, isn't it? But to the same LLM, you add MemGPT, you see it's a game changer. Now it gets it right 2/3 of the time. Isn't that impressive? Now, look at GPT-4. It actually seems to, for a weird reason, have an even worse accuracy than GPT 3.5 turbo. GPT-4 had a 32% accuracy. And now look at the accuracy of the same model with MemGPT architecture. So guys, are you doing any, this is as close as you can come to a free lunch. You're not fine-tuning a GPT. You're not doing anything to the GPT. You're just taking the GPT and reorienting how you use it. Isn't it? It's a change of perspective on how you use the GPT, how you use the language model. And see, to go from 32 to 92, I don't know. I consider that jaw-dropping, isn't it? Right. This is it. Likewise, GPT 3. The latest GPT-4 turbo, right? And look at these numbers. At 93.4, it is usable for long conversations, isn't it, guys? Would you agree that this makes it into something you can build a long conversation chatbot with it? That is it.
Can I ask you? So what is the meaning of it?
No, actually, ask your question. Yeah.
Sorry.
What's the meaning?
When you say 93.4, what is it compared against? Against the
93.4% of the time, it is able to answer what would be considered the gold answer, the perfect answer. Think of it as a perfect answer. I haven't explained how that perfect answer is found or what that gold answer is. Intuitively, the perfect
it's like
answer.
a human numbers.
Somewhere. That's right. Something like that. Now, how that is created, I'll explain in a moment and make sure I do explain. Albert.
So you have this GPT 3.5.
Yeah.
So how do you add the memory GPT in an easy way to?
It's the same architecture. Use it in that framework.
Is there like a prompt? Or
yeah, use the API. Use the API to do that. So the other table is next to it is the conversation opener, right? I suppose you meet a person. How would you start a conversation? Right? Now, each person, you can only do it if you have a long-term conversation recall, right? You have extracted some mental picture of the person based on previous conversations. So there, the human, it turns out, scores, and this part is somewhat even more surprising. This is human on 3 different benchmarks. Look at, right, how MemGPT is able to, when added, like applied to these models. So you have to assume that MemGPT has been applied. It is able to exceed human conversation starters. So the next time you go on a date, instead of coming up with something on your own, use it. Yes. Right, there we go. So guys, now the other one is the document. I think there's a result for documents also somewhere here. I'll come to. Okay, let's go through one benchmark at a time. Oh yeah, deep memory recall retrieval task and consistency, and document conversational opener task. Now let's look at document QA. The bigger the documents become, you realize, guys, that the bigger the documents become, the harder it is to have a good answer from it. So look at the baseline. At this particular moment, if you look at GPT-4, which is, I suppose, your state-of-the-art model, what do you notice? This deep blue line, this line, this line is GPT-4. The accuracy declines steadily, isn't it? It continually declines. For every model, whether it is GPT 3.5, blah, Turbo does better. Do you see Turbo does better? And yet it declines steadily. But what about MemGPT? MemGPT is this line. It almost, you wouldn't have even noticed that line. You would have thought it is the decoration on the graph.
So we should have started this whole bootcamp with this paper so that we would start coding this.
You would actually feel like coding and doing your project. Okay. Guys, when I told you, I don't know, you guys have lost a bit of steam. Do your, see, here's the thing. The AI newsletter agent, see, there are a lot of examples. Creo AI, that have examples of, oh, hey, I can create an AI newsletter. Right? So I started with something that you could find examples for. But if you look at the items that I put in your lab, each item, each thing that I put in your lab, that is curriculum development. I have to think a long time. Let's put it this way. The time that it would take you to do that lab, to do that project, is 1/10 the time it takes me to think through and craft something that will force you to learn every important part of this, right? A subject. So please do that project. For heaven's sake, do it. Right? And look at the kind of question it answers. You ask this question, who won the Nobel Prize, the first Nobel Prize in physics? That is tough. You have to first find out when was the first Nobel Prize given, which year it was given, and look up a table for that subject, isn't it? So archival storage, you search Nobel in physics, you come up with these results. Now, here is the best part of it. And this shows your function calling and all of that in action. And reasoning, the react part of it. What does it do? The Nobel Prize beginning in blah, this award is admits. This is all what? General information about Nobel? Then it basically says, okay, that's not enough. Let's go to page 2 of the results. Right? So the first set of results were not enough. Let's get more results. That's what you do when you browse the web. Right? And then it comes up with something. And then it says the Nobel Prize in Physics is a yearly awarded given. The 1905, look at this, guys, 1905, this line has to be put together with this line.
1901.
The 1901, and the Nobel Prize beginning in 1901, and the 1901 Nobel Prize was given to this person. Then only by putting these two bits of information together only, you can answer this question. Does that make sense? By the way, what was this guy, Wilhelm Conrad Röntgen?
X-ray.
Great, X-ray. Ishla, you had a question? No. Anybody had a question? I saw some hand go up.
So I think this information was there in its database. That's why it could able to search.
It is classic RAG, but it had to do step-by-step thinking.
So the question is, how did it did a page 2 search?
That is what it is. If it doesn't find the answer, it says, get me more.
But
that's part of your system prompt. That's what I'm saying. Write your system prompt properly. I keep on saying that again and
but
again.
the system prompt here also changes, right? Based
No,
on the
it is fixed.
Yesterday.
No, in your
today,
go read the
time
system
was-
prompt. Go read the instruction prompt that it has created. It's very carefully written. And amongst the things it says that if you don't find the answer in the first page, only part of the answer, and there's reason to believe that the other more results may have the answer, ask for more results.
So one question, sorry.
Yeah.
So I promise here the system prompt, generally to send to LLM, but here the MemGPT understand the system prompt also.
No, system prompt is literally the prompt that the LLM deals with, literally internally.
I know, but this is not the LLM.
It is LLM doing function calls.
Okay.
Yeah.
Can we use MemGPT to, let's say, bring up few short prompts from a database to improve your?
That's a very good thought. Actually, Patrick is asking, can we use MemGPT to bring up few short prompts? So basically, self-referential to bring more prompts to improve its own processing. It's a very good thought. I think you can actually do that, Patrick. That could be a research paper. Seriously.
Actually, I was doing something similar like in the ground space because it's also about like can you create a conceptual framework that's easy for like the LLM to. And then I feel like where I kind of have gotten stuck is like at what point do you decide something concept like
Again, Yashila, very good point. Guys, you need to collaborate and write a research paper. Seriously, you're onto something. Seriously, you guys are onto something.
And actually, this kind of relates to like some of the stuff that we've been going over in terms of chain of thought and chain of thought, where they're basically saying that the thoughts in and of themselves are like processable chunks, right?
Yeah.
But then like how do we optimize the chunks to tree of thought?
Right.
That's only the LLM.
Yeah, but like you can use the LLM as a discriminator, but like what's the actual algorithm?
Because you're very useful from A to B, right? And it's the works. But if you have a system that can figure out that this is not good enough, let's add this.
Yeah, and can system prompt be dynamic when as it goes progressive?
No, in this case, they have used static, but that's a point that I guess you guys are all coming to. That what if you could edit your system prompt dynamically, have a system prompt, but have an extra space to keep up, adding some dynamic bits to it by looking up a repository of prompts.
Yeah, it's actually like updating the system prompts and like reference these in space for like all these like space or whatever. But then also like looking at the underlying knowledge graph that you're referencing. Your knowledge graph in and of itself can kind of be seen as like a hash table. A problem that you've never seen before, or a problem that's himself that you're really like then that kind of like you should warrant the hash table being updated so that that has a lot of relevance for that. But like how that is done in terms of like what the updating you should do and so on.
Yeah. All right, guys. So that is very, very nice. And then there's a nested KV. So what they've showed is that not only can they just felt that for this architecture, some of the harder things or these benchmarks, they do so well that they need to create a benchmark that is even harder. Right? And so they create this new benchmark based on KV retrieval, key value retrieval. And that alludes to a little bit to Sachin, what you were talking, but I won't go into it here. Sachin, you have your hand raised. Go ahead.
Yep. So how does this compare to the needle in the haystack that people keep talking about? Is this related to that as well?
See, the needle in the haystack problem is the problem with very large context windows, right? They're lost in the middle. That problem. So here's the situation for very commercial, these ginormous commercial models. The claim is that because of all these breakthroughs like Ring, this and that, Ring attention and that, apparently that problem has been solved. Somebody once said that that professor put all his publications from his lifetime into, I think, Gemini 1.5, and then asked questions and almost always got very precise answers. So to that extent, the needle in the haystack problem might have been solved. Problem here is, see, what is large? Like today, you're impressed by the fact that one whole book can be put, but human mind is like that. The next thing it would say, why can't I have the entire Wikipedia in my context window? Well, then that's a problem. Why can't I have all of human knowledge common crawl in my context window and answer from that? So the large is a relative term, and I suppose in those lens, the needle in the haystack problem, or has it been solved or not? I don't know. I suspect not. Right? To answer your question, the point of this is when you RAG it, even if you have near infinite storage or information, and they use Wikipedia, by the way, when you read this paper, I invite you to do that. You'll see that they have used Wikipedia and they're retrieving information from Wikipedia. In fact, I believe this Nobel Prize, it is literally, if you notice this, this is, oh, sorry, it has been retrieved quite literally from Wikipedia, which is a pretty large data set, which would even, I suppose, even for modern LLMs, this bigger ones, commercial ones, to hold the entire Wikipedia in memory would still be tough. Right? I don't think that the context window is so big they can have the whole Wikipedia. Go ahead, Mark.
So another follow-up question.
1 second, Sachin, hold on to your thought. Somebody with a raised hand for some time.
You should have been changed like some basic context generation, like going something like something.
And keep editing the context. Yeah, that is it. So no, that is built in. Humad's question is, can you edit your archival storage or sort of the context as it generates a token? So the way it works is that it generates a certain amount of token, then it does function. It figures out that is the reason an act. Then it decides whether I need to act on it. And one of the actions it may do is to go edit its context. That's literally what happened here, right? If you look back at its example, that's literally what happened, right? Well, in this case, it didn't happen because it didn't generate something. It got information from the end user, but you can imagine something similar happening, that it generates something and then it realizes that should cause it to go edit its. So that sort of, I would imagine, is implicit in this thing happening. Sachin, I'll come to your question in continuation in a moment. Go ahead, Ishila.
Yeah, just want to Wikipedia. Actually, a lot of the information on Wikipedia can be accessed through like the knowledge graphs that are having building. And that was mostly developed like for historians in the last 10 years because they wanted to look at like the statistics of like, you know, who did this historical figure come in contact with, like what is the likelihood of this kind of thing happening.
Yes.
So it's kind of time for a lot of this LLM stuff because it doesn't require a lot of context.
That is right. That is right. Now you literally gave out one of the projects in my next course. Okay. So anyway, to Yeshila's point, I'll mention that what she says that the behind Wikipedia is a knowledge graph. It is true. There's from the DBpedia, a whole knowledge graph has been extracted. In fact, see, there are not many complete knowledge graphs. There is one that is done by Google, very good. So whenever you search for something on the web page, on the right-hand side, sometimes you see that box pop up. Like you search for something, you don't need to go any further. A box on the right pops up, which gives you all the information for common things. It is actually coming from their knowledge graph. It's pretty good. The only other that I know, a big one, successful, is the Wikipedia's knowledge graph. Tremendous effort has gone into creating it because it used to be a very tedious manual task. They have created it. And obviously now, it is primed for use by architectures like this. Hint, hint, a project.
But also for some context there, if you're like doing projects in like specific like digital communities topics, almost all of them are like knowledge graph-based, like based. So
that I didn't know. She's saying that a lot of projects people do of AI in humanities is knowledge graph based. Oh, that even more increases the importance.
And it's because they can connect it to the Wikipedia database. Like,
yeah. Oh yes, yes, yes. Okay. Sachin, please continue.
Yeah. So the thing is that the Mamba guys were pushing for the large context, right? And I think Google basically said that the 1.5 million or something context length that they either demonstrated or there's a paper, I don't know, where they said that you don't need to make changes so that it can handle it. So is that because this doesn't talk about Google, right?
Yeah, see, Sachin, there we are going off on a little bit of a tangent, but I'll address your question. See, Mamba is a beautiful architecture, right? And a new way of thinking. People are trying to rethink. Everybody wants to solve the quadratic problem, K dot U. The K dot Q problem, right, in the attention equation. So Mamba is certainly much more efficient in that respect. The problem that people face with Mamba is, and the states, the selective state space models, is that empirically they found that for in-context learning or in the prompting, it is inferior to a transformer. Transformers do that better. And also its ability to remember long context windows is not as good. Recently, people have come up with Jamba. So they put Mamba with attention, right? And still manage to keep the performance but they apparently have hit or fixed some of the limitations of Mamba. Then has come, see, developments are happening pretty fast. Then there's ring attention and all of this that tries to fix the context window length problem. Recently, Google has come out with a paper on Hawk and Griffin. Right? And that I think Praveen mentioned. They use ring attention, yeah. So that says that, hey, ring attention, but also they also bypass the transformer architecture completely. So Google created the transformer architecture. Now they have Griffin, which apparently bypasses the transformer architecture. I haven't read the Griffin paper. I would love to read it. It's part of my weekend reading project. But does it, like, how big a deal it is? The jury is out there. I saw some comment, people complaining that when they did the benchmark against Mamba and saying Mamba is better than Mamba, they happened to use a different data set than what Mamba used. And so people are not too happy about that. Well, I don't know what the current situation is, or time will tell, I suppose. And I certainly wouldn't want to comment on that till I've read the papers, read that paper, the Hawk and Griffin paper.
Thank you.
So that's that. Okay, guys, so I'll end this paper reading. I suppose we have talked a lot about it. May I invite you to carefully read this paper? It's really worth reading. Please go and read this paper and over lunch. And then in the afternoon, as I said, we'll do 2 more paper readings. I'll post a quiz to this just for making sure that we understood this paper well. And let's take a lunch break. I'll end the recording now. Any questions before I end the recording? Oh, Krishnan has a question.
So what, is the RAG sitting parallel to this?
RAG, it sits upon RAG. So whenever you go into archival memory, it is RAG.
The functions can use it.
Exactly. You're fetching it back into the main memory. No, the main, think of it as bringing it into the processor is the same as bringing it into the context window. All right, guys, any more questions?
So we're going to try this example.
Oh yeah, guys, please at lunchtime, go to the MemGPT. They have a whole website now. They have a project. You could at least, and it is very well documented. See, guys, this is research at its best. An elegant idea that is easy to understand, right? Brilliant idea that's easy to understand, has a huge impact. The guys who created it have very helpfully written excellent documentation and built a very good project on it and open source the code. And there are a couple of examples. So guys, please go try those examples.
This connects a lot.
And it connects a lot of things. Yeah. Yashila.
I feel like a really cool part about this is that with the RAG functionality, you can also be pushing like the data real time from the conversations into like a pooled data set. So if you have multiple conversations going on at the same time, you can be pulling from other conversations like the things having. Of course, if it's sensitive, then
Yeah, you could have a multi-agent behavior. Yeah, Yashila points out that if there are multiple conversations happening in parallel, imagine that your storage is being enriched with that. And so one conversation can benefit from what's happening in the other conversation.
Yeah.
That's a very interesting thought.
Also, what happens is,
All right, guys, I'm stopping.